In the previous section, we looked at the Taylor series, and the Taylor series is a way to approximate a function. We're going to dive a little deeper into that today, and we're going to look at Taylor series and how they converge. And we're going to start with this theorem here, which is Taylor's theorem. It says, if f and its first n derivatives are continuous on a closed interval between points A and B, and the nth derivative is differentiable on the open interval between A and B, then there exists a number C between A and B such that we have this formula here. And what's happening here is f of b is being defined as a Taylor series around the value a. So we've got f of a, f prime of a times b minus a. So this should look familiar here. Plus then we have this remainder term, which is going to be the n plus first derivative, but now it's at a point C. This really is just a generalization of the mean value theorem. So we have this point C that's going to serve as a remainder term. If we take Taylor's theorem and let A be a fixed point, let B be our independent variable. So in other words, we're going to replace B with X. We have Taylor's formula. And Taylor's formula says if f has derivatives of all orders in an open interval containing A, then for each positive integer n and for each x value in that interval, we have the function f of x defined by that Taylor series out through the nth derivative plus that remainder term. And that remainder term is defined the same way as it was in Taylor's theorem. So we call it the remainder of order n. So again, we're using this as a way to approximate a function. So I've got a note here that says, when we state Taylor's theorem this way, the way it is here at Taylor's formula, we can say that for each x in this interval I, f of x is the Taylor polynomial of order n, and that's what we get here with these first terms, plus that remainder of order n. Now, we're going to extend this, and this is where we're going to look at the convergence. If that remainder term, that remainder of order n, if that goes to 0 as n goes to infinity, we can then say that the Taylor series that's generated by that function f is going to converge to f. So we're able to define that function by its corresponding Taylor series. And there's going to be times where this is going to come in very handy, and we're going to be using these Taylor series which are, again, approximations, but there are certain circumstances where they're going to come in handier than actually using the function. A lot of times this is used in more applications. So looking at maybe the physics side of things, or even in engineering, where you're looking at more applications of calculus, this is going to come in very handy. What this gives us are a few useful series. So I have here the number e as a series. So e, which is approximately 2.7, can be defined as the series that goes from n equals 0 to infinity of 1 over n factorial. As a side note, e to the x can also be defined as a series. It's the series from n equals 0 to infinity of x to the n over n factorial. And these are going to come in handy. We're going to work some examples where we're using some of these. On the next page at the top, Sine and cosine can also be defined as series. So sine and cosine are both alternating series. Sine is an odd function, and you can see it here. It's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. Cosine is an even function, and you can see it displayed here as well. So what we're going to do is we're going to use these series, and we're going to use them to find Taylor series of slightly more elaborate functions. Now, I'm going to do 2 examples in this first video here, and it says use substitution to find the Taylor series at x equals 0 of the following functions. Now, in the previous section, we looked at the natural logarithm of 1 plus x as a series, and we also looked at 1 over 1 minus x as a series. And I'm going to use that with these first 2 examples. So the first one here, and again, I'm going back to section 10.7, the natural logarithm of 1 plus x is equal to the series that goes from n equals 1 to infinity, and it's negative 1 to the n minus 1 times x to the n over n, and it holds for values of x between negative 1 and 1. So I want to find the Taylor series here for 1 plus x squared. So what I'm going to do is here, in place of the x, I've got an x squared. So over here in the sigma notation, I'm going to replace that x with an x squared. So we're looking at the series from n equals 1 to infinity of negative 1 to the n minus 1, then x squared to the n over n, which is just that series for n equals 1 to infinity, negative 1 to the n minus 1, x to the 2n over n. And the first couple terms of it, for n equals 1, you're going to have x squared. For n is 2, it'll be minus 1/2 x to the 4th. For n is 3, it'll be plus 1/3 x to the 6th, and so on. So there, we just used this known series to look at this slightly more complicated one. And I'm going to do the same thing here with the second one. So we have 1 over 1 plus 3/4 x cubed. So again, from the previous section, we know that 1 over 1 minus x is equal to the series from n equals 0 to infinity of x to the nth power, where the absolute value of x is less than 1. It's just a geometric series there. So this should look familiar. It's just the sum of a geometric series. So we're going to take that and use it to help us here with this function. So I can rewrite the given function as 1 over 1 minus negative 3/4 x cubed. So instead of just having x to the n, I'm going to have negative 3/4 x cubed to the n. So as a series, it's going to go from n equals 0 to infinity, and I'm going to have negative 3/4 x cubed to the n power. And we can break this into pieces, if you will, so I can rewrite this as negative 1 to the n power, 3/4 to the n power, and then x to the 3n power. So there would be our series. And again, we're looking at a simplified version. The 0 here is referring back, let me scroll back, to that value of a. So here are the first couple terms. We're going to have a 1 when n is 0. Then it's going to be minus 3/4 x cubed. Then it'll be plus 9/16 x to the 6th, and so forth.